We have contemporary automatic program analysis with Julian. Please enjoy.
Thank you. It's an honor to speak here at Black Hat today. Hope you guys enjoy the talk. So I'm Julian Cohen. Aside from my full-time job doing application security at a large university, I teach a course at NYU. I help run an event called Cybersecurity Awareness Week at NYU. I'm an advisor to the ISIS lab, which is an offensive research lab at NYU. I help run a CTF competition called Ghost in the Shellcode, and I'm a moderator for RNetSec and RVRD. And I'm part of a group called NISEC, which is the New York Security meetup, which is the New York Security CitySec meetup. Just really quickly, I want to tell you about this event called Seesaw that we run every year. I think it's really special and not a lot of people know about it. It's a student-run event at NYU Poly. It features 6 competitions where we have over 10,000 people from all over the world compete in a variety of different competitions. We have a cybersecurity-focused career fair where these really great companies come to hire the finalists from all these competitions. We have really great talent, plus really great organizations hiring. It's an amazing event. We have a conference. This year it's focused on security automation, and for no other reason, it's a great excuse to come to New York City. Program analysis. I always say the first thing you have to do before you have a meaningful conversation about something is define what you're talking about. So here's some definitions. When I say program analysis, what I really mean is just code that analyzes other code. And we're going to talk about this a lot, and this can mean like a whole lot of things. And I have this little graph which shows some of the things we're going to be talking about today and where they fall on this in between static and dynamic and manual and automatic. So unfortunately, I'm going to have to be ambiguous at some parts during this talk, and I do this for 2 reasons. The first reason is I don't want to impart too many of my ideas about program analysis into you. If this is like the first time you're hearing about program analysis, if you're not familiar with program analysis, I don't want my beliefs to be imparted on you, so I'll be ambiguous when I think being explicit will be detrimental to your thought experiments, and I'll be ambiguous when I feel that being explicit would be giving too much information to the bad guys. So feel free to use your imagination throughout the whole presentation. We're talking about using program analysis to aid in vulnerability discovery. But vulnerability discovery is part of a much bigger process which we call vulnerability research. And I like to break down vulnerability research into 6 steps. The first step is reconnaissance. After a target is picked, some recon is done, looking for information like how the target is built, how does it operate, where are potential entry points or weaknesses. Then we start looking for vulnerabilities, and that's what we're going to focus on today, how we find vulnerabilities using program analysis. After a vulnerability is discovered, it's typically analyzed. So we're looking for what are the properties of the vulnerability, how long will it take to weaponize the vulnerability, how easily fingerprintable is it, how difficult is it to discover and patch. Then an exploit is written. The development stage can also include shellcode and malware development. Then we deliver the exploit to the target. This step includes everything needed to get code execution on the target. It can also include a phishing email or watering hole attack to make sure the exploit lands on the target. And then the final step post-exploitation is when some goal is extracted from the target. This can include command and control, lateral movement, data exfiltration, all this kind of stuff. So vulnerability discovery, which is what we're going to be talking about today. There are 2 main methodologies for vulnerability discovery. Manual auditing, which is auditing, reading code until a vulnerability is found. Just reading like either source code or native code or some kind of code until you find a vulnerability. Or automatic testing, which is typically referred to as fuzzing, until a vulnerability is found. So you have some kind of automated tool to run the program with either different inputs or different environments, and you wait till it crashes, or you notice some other external behavior that lets you know that a vulnerability has occurred. But I always like to say that a best approach is a combination of these two. You want to let your manual findings feed your automatic testing, and you want to let your automatic findings feed your manual testing. For example, if you find a function that looks a little complicated while you're manually auditing, you want to make sure that your fuzzer can reach that function. And if your automatic tools output a false positive that looks interesting, you want to make sure you go and look at that manually to see if there's any other issues there. So if your job is to find bugs, you probably already use some amount of program analysis. My goal in this presentation is I want to show you some really simple tricks that you can use to find interesting vulnerabilities, and I want to introduce you to some program analysis tools, techniques, methods that you can use to make informed decisions about finding bugs in your organization. So let's jump in. So we're going to start off with meta-character injection vulnerabilities. These are really easy to find and exploit. They're so easy to find, finding a couple of them wasn't good enough. The first tool we're going to talk about is a tool called GitHub grep.py, which I wrote a couple weeks ago. And it's a very simple script that just automates queries to the GitHub code search. The user provides functions, input, and security keywords, and the script creates queries based on those keywords and sends them to GitHub, receives the results, and then outputs how many vulnerabilities each query found, and gives you a link to go view them on GitHub. Everyone's seen this kind of thing. You know, you type RSA private key into the GitHub search, and RSA private keys pop out because users committed them without thinking. So the reason why we use the script instead of doing it manually is the GitHub code search only allows you to have a certain number of modifiers per query. So if we build this really long query string that we want to send to GitHub code search, it'll just return saying your query is too long, or your query has too many modifiers. This script has a low false positive rate because we take into account sanitizer keywords, and you'll see what I mean in just a second. So this is what it looks like when you run the command, when you run the script. You specify a language, some functions, some sources, and sanitizers. So here we're finding command injection vulnerabilities in PHP. There are like hundreds of ways to execute commands, shell commands in PHP. But for this exercise, I just opened up one of the PHP documentation pages and just wrote down like one of the, it was like a, how to execute shell commands in PHP, one of the documentation pages. And I just picked all the functions that they listed, put them here, exec pass-through, shell exec, system, and popen. And I picked the obvious sources of input, request, the globals request, get, and post. And I picked the two sanitization functions that were also listed on that documentation page, which were shell escape command and shell escape arg. And then we have this, we have this command that we can run. So this resulted in 1.5 million vulnerabilities. And we know that there's a low false positive rate here because GitHub's not going to return any results that have escape shell command or escape shell arg in the entire source file that it's searching. So all of these results don't have any sanitization at all in the whole file. And we can see this is just a sample of some of the results, all obvious. Command injection. So here we do the same thing, but we're looking for cross-site scripting in Java. I did the same thing. I opened up a documentation page, like one of the request objects, and I just typed in the functions and the sources and the sanitizers that were listed in that request object, and we found 750,000 vulnerabilities. And you can see the same thing. clear cross-site scripting vulnerabilities. So the next thing I want to talk about is type confusion vulnerabilities. Type confusion vulnerabilities look different in different languages, but in C and C++, they usually look like this. So what we have here is a union, which is a language construct in C that says that everything inside of the union should be stored at the same place in memory. So that doesn't mean near each other in memory, it means in the same place. So an integer and a char pointer on 32-bit systems are both 4 bytes long. They're actually going to be stored in the same location, in the same 4 bytes of memory. So if we read from the network into number 4 bytes, and we treat that's treated as an integer, and then we then reference buffer as a pointer, they're going to be the same memory. So the 4 bytes that we read into number are going to be used as an address to a string in str copy, and we're going to be reading user input into an arbitrary location for whatever length buffer is sized. Does that make sense? Okay. So we have an arbitrary write vulnerability here because of the type confusion between the integer and the char pointer. This is a vulnerability. So this is a type confusion vulnerability that Chris Rolfe, one of the guest lecturers for my course at NYU, found during a manual audit. And here we have just using grep in the file where the vulnerability was found, and we can immediately see that it's easy to find, and we can also see that there's probably a problem here because there's a pointer listed in the union, which you want to be careful about. It's easy to find this bug because of the union construct. And in this example, I just searched one file, but we can search an entire code base and look at all the unions that the developers used and see if there are any vulnerabilities in there. So using grep has a very high false positive rate. It's only effective when you know exactly what you're looking for, like a type confusion vulnerability, but it still can be useful. And there's just one example of showing how using grep can be useful. The next thing I want to talk about is implicit type conversion vulnerabilities. This is a pretty common thing you see in C and C++. So here we do the same thing. We read 4 bytes into size from the user, and we test size against a constant. So if size is less than 100, we're going to stir copy into buffer. And buffer is 128. So this looks safe, right? But the problem is size is a signed integer. 100 is a signed integer. But the third parameter, stir copy, is an unsigned integer. So if we pass in a very large integer, if the user passes a very large integer into over the network, the signed integer will be casted to an unsigned integer, and we're going to have a very large copy into buffer, causing a buffer overflow. Does that make sense? Okay. So turns out this is also really easy to find. If you have source, most compilers will just spit this out to you if you ask for it. -w conversion is to show you all implicit type conversions in your source code. And so in this example, implicit.c is just this code, and it shows us that we see a conversion to the unsigned integer, which is size t, from the signed integer size that we got from the user. And it gives us a pointer to the line of source. So on my Ubuntu VM, W conversion was not included in WAll, but someone on Twitter said that they found it using WAll. So the next thing I want to talk about is buffer overflow vulnerabilities. Here we have a very simple example. Buffer is 128 bytes long, and we unbounded stir copy from input into buffer. If input is bigger than buffer, we'll write outside the bounds of buffer and end up with some kind of issue. I want to introduce a tool called RATS. You might remember RATS. I think it's over 15 years old at this point. RATS uses simple static analysis to find potentially vulnerable code. It analyzes C, C++, Perl, PHP, Python, and they're adding support for Ruby. The way RATS works is it parses and tokenizes source code, and it checks variables, identifiers, and comments against a set of rules that ships with RATS. It has a high false positive rate, but usually every finding is worth looking into because of its rule checking. So here I'm running RATS on a library called MozJPEG, which is Mozilla's fast libjpeg library, which they actually forced from libjpeg-turbo. And we found there were a lot of results, but we found these two stir copies. It took about 5 seconds for RATS to run and print out all these results, and it took about 15 minutes for me to go through the results very quickly and find the two vulnerabilities that were output in the results. As I was going through the source code, it became very apparent that MozJPEG and libjpeg-turbo were written very well. But when I got to this piece of code in wrjpeg.com.c, it was clear that very good coding style went away. When I submitted this bug report to libjpeg-turbo, they informed me that this code was came from upstream, which was the reference implementation for JPEG. And when I sent them an email, the quote I got from them was, the wrjpeg.com.c source file has not been changed since 1997. So this is the code. I just want us to look at it really quickly. This is the two vulnerabilities are right here in these 10 lines of code. What this code does is it parses the argument that's passed after -comment. And so the first two arrows are the first stir copy vulnerability. Max com length is set to 65,000. And then we stir copy the argument into comment arg, which is 65,000 bytes long. And if we supply an argument longer than that, we'll have a buffer overflow on the heap. So this particular piece of code was only expected to run on Windows, but we can force it to run on Linux just by making sure our first character is a quote, and that's the if statement right above the first arrow. And on Windows, 65,000 is the actual max length of an argument, but it's not on Linux. So the first bug, the unbounded stir copy into comment arg, which is a fixed size buffer on the heap. And the second bug, the two stir cats, which are unbounded into the same fixed size buffer on the heap. So what's basically going on here in this for loop is if there are more comments after the -comment that aren't other switches, just keep appending them to the same buffer. And we can, obviously it's a problem. But so this is easy to find if we have source. This would be easy to find manually auditing. It's easy to find with RATS. But let's say we don't have source. How could we find this vulnerability? I want to introduce valgrind memcheck. Valgrind uses dynamic binary instrumentation, which just means that when the binary is run, it opens the binary and makes some changes to the native code while it's in memory. It rewrites, in particular, it rewrites this code to instrument memory operations. Memcheck tries to find all memory operations to make sure that they're safe. And it reports any invalid memory operations. It has a very low false positive rate because almost every report that it spits out is an invalid memory operation, and which means it's a bug. The main problem with valgrind is that it's pretty slow. And the other problem is you need test cases to exercise each vulnerability. If you don't have test cases, it won't know that the memory operation it won't know that the memory operation could ever happen. So this is us running valgrind on wrjpeg.com, and we pass in 70,000 A's after a single quote, and it exercises the code path we just looked at, and it tells us we have an invalid write of size 1 in stir copy to this buffer on the heap, which is at OX52 something, which is supposed to be 65,000 bytes long. So it knows that the malloc was called with the argument 65,000, and it knows that stir copy is writing byte by byte into that buffer, and when it reaches the 65,000 and first character, it immediately tells us, oh, we wrote past the end of this buffer. So that's super neat. Here's the same thing for the second vulnerability. Here we pass in a 60,000 byte string of A's plus another 10,000 string of A's. And so we exercise the second code path where it's reading the second argument to the end of the first, appending the second argument to the end of the first argument on the heap. So we see the first, we actually see in this iteration, we see both stircats, both calls to stircat, creating output here. So let's flip back really quick. So there's two calls to stircat, one with an empty character and one with the whole second argument. And it prints out both of them here. So more of the same information, invalid write of size 1 because stircat writes byte by byte. And we see both of them, and it gives us all the information we need to go find that vulnerability. But let's say we don't have test cases for this vulnerability. How can we find it? So I want to introduce a tool called QuickSec. QuickSec is a simple static analysis tool for native code. It's written in IDA Python. It's written by Kevin, who's sitting right over here, a student in my class. It's very similar to RATS in that it parses and looks for function calls, but instead of in source code, it looks for it in binaries. It also attempts to determine the vulnerability of its findings. It'll try to use information provided by the binary and by IDA to determine the size of buffers and if the buffers are fixed size. It has a very low false positive rate, just like RATS, and every finding is usually worth looking into. So when you run QuickSec, it runs an IDA. It looks like this. Whenever it finds a potential vulnerability, it'll mark it red, and it'll give you an address to go look at it. Yeah. So, quick kitten interlude. Now we're gonna get pretty serious now. So the next thing I want to talk about is use after free vulnerabilities. Memory allocators make no guarantees about the state of memory after it's been freed, obviously. Typically, your memory allocator documentation will tell you to expect that your memory is gone immediately after it's freed, but this is rarely the case. However, after memory has been freed, it can be reused by another object. So here in this example, we free a pointer, and then we call a function on this pointer, and if another piece of memory has been allocated in the space of free memory, this function call can fail or do something unexpected. I want to talk about the Aurora use after free vulnerability in particular. In 2009, a sponsored group used the Aurora vulnerability to break into Google, Adobe, Juniper, Rackspace, and a bunch of other organizations. And so from information that was from analysis of the Aurora vulnerability, it was simple to tell that what was going on here was a use after free vulnerability, and they were calling a function from a C element, or from a C tree node rather, which had a reference to it from an event param. And further analysis showed us that the reason that event param had a reference to this freed C tree node was because the copy constructor for the event param was compiler generated, and it was doing a weak copy of the event param. So in the second slide at the bottom, we can see that C tree node has a ref count of 2 from the event param pointing to it and from the C element from pointing to it. And then when we make a copy of the event param, the copy constructor is called, and we make a third reference, but the reference counter isn't incremented. And then if we remove the original event param and the C element, then and the C tree node, we remove the event param and the C element, the ref count of the C tree node goes to 0, the garbage collector cleans it up, but we still have a reference to it from the second event param. And then we can use that reference to call functions on it and to access memory from a freed location on the heap. So the reason this vulnerability existed was because of the compiler-generated copy constructor. So if we can find all compiler-generated copy constructors, we can find vulnerabilities that look like this. And that's exactly what Aurora UAF does. It checks for compiler-generated copy constructors. It uses IDA to find all the copy constructors in a binary. It demangles their names, and it looks for a rep move SD instruction. And Visual C++ used the move rep move SD instruction for shallow copy constructors. It has a low false positive rate, but also has a high false negative rate, which I'll talk about in a second. I'll talk about it right now. It has a high false positive rate because copy constructors are often inlined by the Visual C++ compiler. So when you run it on mshtml.dll, it looks like this. It prints out all the copy constructors that it thinks are compiler generated. And this is an old version of mshtml.dll. So we see the event param show up, and it tells us the address of it. We can go and inspect it and see that it actually is compiler generated, and there's probably something there we should look closer at. It's not always perfect, but it works. And keep in mind that we missed out on a large amount of copy constructors because they were inlined by the compiler. And if we were to do a wider analysis of the whole binary, we might find some more stuff. I want to introduce a concept called symbolic execution. Spend a little while on this slide. This is a simplified version of an example I stole from Harvard University's Advanced Topics in Programming Languages course. The green boxes in the graph are the current state of the program. The blue boxes are decision points where we would take one path if we were doing concrete execution, but where we can take all paths in symbolic execution. And at the bottom, the orange boxes are the path conditions. So this code is pretty simple. We treat A as symbolic. You can think of A as input to the program. And based on the value of A, we set X and Y. So if A is more than 5, we set X to 1. If A is less than 12, we set Y to 1. And at the bottom, we assert that X plus Y is not equal to 2. So we treat this assertion as if the assertion is true, something is wrong. Like maybe a vulnerability would occur or the program would fail or something like that. So we want to see if we can find any values of A which will make this assertion fail. So we use symbolic execution to do that. And so we have in the tree, when we reach the decision point, alpha is more than 5, we have two possible paths. Either alpha is more than 5 is true, in which case we set X to 1 and continue, or it's false, in which case we don't set X to 1 and continue. We do the same thing for A is less than 12. And if A is more than 5 and less than 12, the leftmost path, we reach a state where X is equal to 1 and Y is equal to 1, and we reach the path condition, which is what I just said. A is more than 5 and A is less than 12. And the assertion fails, and that's interesting. Any questions? Okay. The next thing I want to introduce is constraint solving. So here we took the path constraint from the previous slide. Alpha is more than 5 and alpha is less than 12. And we want to do two things. We want to determine if this equation is satisfiable or if it has a valid solution at all. And that would tell us if we can ever reach this state of the program where X is equal to 1 and Y is equal to 1. And the second thing we want to do is we want to find a valid solution, which would give us a concrete value for alpha, for A, that we would be able to use as input to the program. Z3 is a theorem prover written by Microsoft. It interprets common Lisp S expressions, which are these expressions in parentheses using prefix notation. So the operator is the leftmost parameter. There are also Python bindings for Z3, which I'm told are very, very easy to use. So on the left, what I do is I create a Z3 program that defines this equation. So we declare a constant a. We assert that a is more than 5 and a is less than 12. And then we want to check the satisfiability and get a model that tells us, that gives us a valid solution. So Z3 returns that it is satisfiable, or returns sat, and it gives us a model where a is equal to 6, which is more than 5 and less than 12. And we can now run the program with 6, and it'll reach the assertion and crash. So now I want to introduce a tool called CLI, which is written on top of LLVM, and CLI does exactly what I just described. It's an automatic test case generator. It uses symbolic execution to explore potential states of the program, and then it solves the constraints that it finds and generates test cases to increase code coverage. CLI is excellent at increasing code coverage. That's what it does, and generating test cases that you can use to either feed your fuzzer or just run to see if the program crashes. CLI requires source code or LLVM bitcode. So here I took the program from a couple slides ago, modified it slightly, and so modified it slightly so we can use it without calling assert. So we have if x plus y equals 2, we're going to return -1, and if else, we're going to return 0. We also use this function called CLI make symbolic, which tells CLI that the variable a is input, and it should treat it as symbolic input. So when we run CLI, it looks like this, which I'll show you in a second, and it prints out all the test cases that I found. So I found 3 test cases, 3 possible values of a that give you different code paths through the program. And here's just an example of the first test case that printed out. It tells us a, which is an integer 4 bytes, and if it has the value of 0, it has one path through the program. So now I'm going to show you a demo of using CLI. Okay. So this is the program that I just showed you with more new lines in it. And here are all the test cases that CLI generated. So the first test case, a, size 4, is 0. The second test case, a, size 4, is 2 billion. And the last case, a, size 4, is 6. Actually, I'll just run CLI for you real quick, so I'll show you, see how fast it is. Obviously, it's a very simple program, but it's still very fast. That's it. It's done. So we can also use CLI to run the program, the real program, with the input that CLI generated that provides a different code path. So what we do here is I just passed a test file that CLI outputs as input to the program, and we can see that we know that the first test case was 0, and that'll make the program return 0, and we see that the program returns 0. And the second test case also returns 0. And And the third test case, which was 6, more than 5, less than 12, produces -1, which is 255. That's that. So there's a lot of stuff that I wasn't able to cover today, and I want you guys to know that they exist so you can either look at them on your own time or just know that they exist. So in terms of symbolic execution engines, there are a lot of these. S2E is very popular. The Clang, the C-Lang static analyzer is popular. It's the C-Lang static analyzer is popular for the same reason that CLI is. It's built on top of LLVM, and it it can use all the powerful insight that CLI is able to look at. Andrew Roof, who was one of the guest lecturers for my course, wrote a C-Lang static analyzer checker to find the heartbleed bug in OpenSSL, and it's open sourced on GitHub. Immunity Debugger also has a bare bones symbolic execution engine built into the Python libraries inside of Immunity. CLI, which you just saw, Fuzzball is built on top of BitBlaze, and FuzzGrind is a fuzzer that uses symbolic execution and constraint solving to automatically generate new test cases. And it's been used to find bugs in Adobe Reader. In terms of constraint solvers, there are a lot of these too. Cleaver is CLI's constraint solver. CLI is also written to use STP, which is another constraint solver. People taking pictures. The next thing, binary instrumentation engines. We talked about Valgrind. There's also Pin and Dynamo Rio, which allow for very powerful dynamic binary instrumentation, change the programmatic changing of native code during runtime. Static analysis platforms, we talked about IDA-Python, but there's also a lot of other powerful static analysis platforms. Something that's gaining a lot of popularity is a platform called BAP, or Binary Analysis Platform, written by the team at Carnegie Mellon. It has its own intermediate representation, has a lot of tools to allow you to change code and analyze it in different ways. Insight and JackStab are similar to BAP. Stack is an MIT project. I think it's fairly new, and it's focused on finding undefined behavior in C programs. VCC is a Microsoft project, and the way it works is you provide preconditions and postconditions to different functions of your program, and it'll check to make sure that your code matches those preconditions and postconditions. And if something doesn't match up, it'll tell you during compilation. So I hope I demonstrated that program analysis is powerful. It can help you find vulnerabilities very quickly and at very low cost. The goal of this talk was to introduce you to this stuff, and hopefully now you can follow up on some of the concepts I introduced and play with the software I talked about and develop new tools, techniques to find vulnerabilities and improve the way that you find vulnerabilities in your organization. Thanks. I want to thank a couple people, Andrew, John, Julian, and Chris Rolfe, for guest lecturing my course. They taught all the parts of the course that I wasn't qualified to teach, and without them, we wouldn't have had a course at all. I also want to thank Jolly, Ben, Chris, Kelly, and Jen for supporting me while I was writing these slides, Pound BAP on Freenode for their expertise in trivia, and the students of my class who are the inspiration for this talk. I also want to thank these folks who I consider mentors and friends. And do you have any questions? Yes?
So, I noticed in your list of static analysis tools, I didn't see anything like Coverity or considered as static analysis.
No, so the question was, we didn't see Coverity in the list of static analysis tools. It definitely counts as a static analysis tool. Just for the purposes of this talk, I was trying to focus on open source stuff. Yep.
Talk a little bit about the trends for higher level languages.
Say that again?
Trends for higher level languages like MSIL or the Java language.
The question was trends for higher level languages like C#. I would say that all the techniques that we talked about are applicable to these languages. I know in particular for the Microsoft intermediate language, there are tools like .NET Reflector, which will automatically take your compiled C# code and bring it back up to C# for analysis. In terms of automatically finding vulnerabilities, I'm not aware of any tools, but I wouldn't be surprised if there were similar tools. Yes? Sorry. See, the question was no love for formal verification. I wanted to put formal verification inside. I felt that it was a little heavy for the talk, and I didn't know that I would have all this time at the end. I apologize. Yes?
I'll go with that one. This is Black Hat, not Sands. I'm just going to say I agree with him. This is Black Hat, not Sands.
Okay. Black Hat, not Sands. Yes. Next time, I will add formal verification. Any other questions? All right. Thank you.